in front of you until we're done with this, that will be just fine. There were two questions to answer, and the first question was, find the probability of a particle in a box, rigid walls, of course, a box of dimension L. Find the probability of the particle between 0.45 L and 0.55 L. The second question was, find the expectation value of the particle. Same particle, same box. And in both cases, I wanted you to consider the ground state, the lowest energy allowed, and the first excited state, the next higher energy allowed. Also, at the bottom, I wanted you to discuss, and really what I wanted you to do was to think a little bit about the difference between the two answers, what do they mean, and compare your results to classical physics. Now, in classical physics, if we imagine a particle in a box, here's the one-dimensional box. B equals infinity. Infinitely large walls. So this is energy, space, x equals 0, x equals L. If you imagine a particle in a box, first thing we learned was, of course, it cannot be stationary. It's got to have some energy. So, at this moment, I don't care what energy it has some energy and it's bouncing back and forth. Elastic collisions at the walls, so the particle does not change velocity, it's just moving back and forth with constant speed. So, it spends equal time everywhere. In the center portion of the box, from 0.45 L to 0.55 L, that is 10% of the box. The particle should spend 10% of its time there. That's what we expect, classically. Because the particle is just going back and forth at constant speed. 10% of the box, 10% probability of finding it there. That's what we expect classically. So what do we expect classically? The interval is 10% of the box. It's centered on the middle of the box. Therefore, we expect it to be there 10% of the time. Now, according to quantum mechanics, we find that the probability, and let's start with the general definition, probability is equal to the integral of psi squared dx over the interesting limits between x1 and x2. So the probability you're going to find the particle between x1 and x2 is the square of the wave function integrated over that part of the interval. So, as several of you asked this morning, well, what was the wave function? It's a particle in the box. It's the problem we solved on Monday. So, psi was root of 2 over L times the sine of 2me over h bar, this is under the square root, x. And then when we inserted for the specific energies, when we put in for E sub n, we came up with a psi sub n, which is, of course, the same normalization constant, 2 over L, square root, sine, and then we had n pi x over L dx. So, here's the generalized wave function, but we're interested in certain specific energies, so we put in the specific energies, and that gives us a specific wave function. So what I did was to integrate from this point and insert the appropriate n values at the appropriate locations. So, my integral tables tell me the integral of sine squared ax dx is given as x over 2n minus 1 over 4a times the sine of 2ax. And for us, of course, a is going to be this part right here. That part is a. N pi over L. That is our K. So our probability, which is going to be the integral of this creature squared, will of course bring the 2 over L out front, since it was squared.
How do you size that instead of just sine?
Because I've asked you specifically for certain energy levels, in particular n equals 1 and n equals 2. So you've got to give 2 different answers for those 2 specifics. Therefore, we need the specific wave function that goes with the specific energy. Make sense?
Yep.
Okay, good. Where am I? I'm lost. So we bring that out front, and it's of course going to be multiplied by x over 2. And for us, that is of course x over 2. Minus 1 over 4 times a, which is n pi over L, times the sine of 2a x evaluated between 0.45 L and 0.55 L. Yes, we do have n's here and here, so to get a specific answer, so probability n equals 1, let me maybe put it up here, okay? So the probability n equals 1 is simply going to be 2 over L times x over 2, but we start with the upper limit of 0.55 L divided by 2 minus L over 4n pi. Oops. I don't have to put n, do I? I just decided n equals 1. So it's now 4 pi. Where am I? Right there. Times the sine of 2 pi x, which is 0.55 L, divided by L, minus, and then all we're doing is putting in a 0.45 L here and here. The n is the same, everything else is the same, so it's going to be 0.45 L over 2 minus L over 4 pi sine of 2 pi times 0.45 L over L and of course, nicely, all the L's disappear, so it doesn't matter what L
wait, no,
is.
Professor,
Yes, go ahead.
That's confusing to me because the 1L is concerning the length of the box. I thought the other L was talking about the angular momentum.
There is no angular momentum up here. It's all just the dimension of the box. L is used for angular momentum sometimes.
But it's not.
But if you go back to the very beginning, we never mentioned angular momentum when we derived this formula. Never once. And then, of course, this L, let's use another color. This L goes away here and here. And now we're finally down to just a number. And when we insert these numbers into the calculator, I got 0.198. 0.198. That's what I got when I stuck that in there. You can simplify a little bit further, of course. There's a 2 here, all the way across, so you can cut that down a little bit.
Professor?
Yes?
I'm sorry, but the L appears to me when we derived it to have come from En equals n squared over h bar squared pi squared 2mL squared. And in that case, the L was not length, it was angular momentum.
I'll need to look at your notes compared to mine, but no, I never mentioned angular momentum. All I said was, I think what you're looking at, and I'm not sure, but I think what you're looking at is the point where I said that you're at a boundary condition and you must have a node at L. So I was insisting that at L, the argument of sine equals 0.
But L will change depending on n, and because you have more weight, you have a higher angular momentum, right?
L doesn't change depending on n, just how many nodes you have. N is the number of nodes, really. And so the number of nodes changed, but no, all we argued, let's just take it aside now. Let's stop this for a second.
Wait, so L is...
And I think, let me start with what I said to Christina, and then I'll respond to what you're saying now. But we had x equals 0, x equals L, and we insisted that there be a node here and here. Now, before we go on, how do we know, physically, how do we know there's a node at each end? Because the walls are infinitely hard. The particle cannot exist at or beyond the walls. That's the key argument. So, we had, what was it? I don't remember what we had exactly. We argued that at L, there be a node, so the sine, was it? I've forgotten what point we were at when we made that argument. Where exactly?
I found it.
Okay, I'll use your notes, although I'm a little bit. Okay, yeah, okay, so we've gotten there. Thank you very much. So we've gotten to this point. We were at the sine of 2me, 2me under the square root over h bar, L equals 0. We got to this point. Thank you. So when x equals L, it's required that this give us a 0 answer. The way we do that is, of course, to make this part 2me over h bar L equals sine is 0 at any number of pi, right? If it's pi, 2 pi, 3 pi, so on. So we put in n pi. That's the requirement. The requirement that you have a 0 there is this in mathematics. So we just simply solved for what the energy was. Go ahead.
But there's still two different L's though. There's still two different L's.
What two different L's? This is the L for the dimension. There is x equals L.
Right, but when you you substitute in something for E, because you don't want E, because you can't solve for E right now. So you substituted in for E, h bar squared pi squared over 2ml squared, and that L is angular momentum.
All we did was solve for E here. We didn't substitute for E, we solved for it here. Square both sides of the equation, 2me over h bar squared L squared equals n squared pi squared.
Okay.
So now, E equals n squared pi squared h bar squared divided by 2m. Since E depends on n, we put a subscript of n. Okay?
Where's the L?
Hmm?
L.
Where's L? L is coming. L squared.
There we go.
L is just a little lazy. Came a little slower. Okay?
Yeah.
So now this L is still this dimension. What we found was that because you require a 0 here, you get specific energy solutions. Only certain specific energies are allowed. Okay? Now, I was going to answer her first and respond more to what you said. I forgot what you said.
That L would increase as the number of moves increases.
No. And this is all constant. Once you fix the box, this is constant, so as you increase n, you increase E sub n. So the energy goes up as the n goes up. So if n goes to 2, then E sub n is 4 times what it was before. If n equals 3, it's 9 times what it was before. That's all that says. It does not change L. L is fixed. These are good, important, key questions. Are there any others? These little steps will kill you if you don't have them right. Right? So that's why I'm really pleased you folks are asking these questions. These are the key questions. Is there anything else? Of course it's going to be Christine.
I'm sorry, why again can we say that the square root of 2me over h bar is equal to n pi?
Say it again.
Why can we say that the square root of 2me over h bar L is equal to n pi?
What we're saying at this point, we start here. Do you agree with this?
Yeah.
That we must have a 0 when x equals L. Okay? They're not asking about that though, are you? So we say, how do you make sine equal to 0? If the argument itself, the argument of sine, is n pi. Anytime sine of 1 pi, 2 pi, 3 pi is always 0.
Oh, yeah.
So that's how we get from here to here, is saying, well, the only way we can get a 0 here is if this whole thing is equal to some integral number of pi.
Just a dark sine of both sides.
Just correct what?
Just a sine inverse of both sides.
Guys, these are old years.
No, you just a sine inverse of both sides.
The sine is, yeah. Okay, anything else? This is good stuff. All right, now let's continue. We've just gotten to this answer right here. And of course, it's surprising. Doesn't this say 20%? Didn't classically we assume it was going to be 10%? Shouldn't the particle be spending 10%? Right now you're surprised. There's two things. You're surprised. This is utterly different. This is twice the answer that you would expect classically. You're also quite delighted because now, of course, if you can figure out how to do this experiment, you can really tell whether or not quantum mechanics is correct. Because if quantum mechanics is not correct, if the particle acts like a classical particle, you do the experiment, you're going to actually measure 10%, 0.1. But if quantum mechanics is correct, you do the experiment, you're going to get 0.2. And knowing how experiments go, I can distinguish between 0.1 and 0.2, can't I? I mean, if one of them predicted 0.101 and the other predicted 0.102, I don't think I could do an experiment to distinguish between this 1 and 2. Right, 101 or 102, that's hard to do. But if one says 10% 0.1, the other says 20%, that's different by a factor of 2. Clearly you can do an experiment and easily distinguish. So number one, you're surprised. It does not agree with classical at all. But number two, you're pleased because this gives you experimental opportunity here. Now obviously within experimental error, if I can figure out how to do this experiment, I can definitely distinguish who's correct. Does classical predict or does quantum predict accurately? And of course quantum predicts accurately.
Is that because the arc length of the segment of the sine wave changes as you're around different portions of the sine wave? And
Absolutely. And I intend to show you that in just a couple of minutes, but absolutely, you are correct. Let me show you that after I solve the second part of the question. And that is where n equals 2. What happens when n equals 2? Well, all you do, you take the same basic solution and you put a 2 here and here. But the 0.45 and the 0.55 stay the same. So the probability n equals 2, it's the same basic solution as I said with a 2 here and here. Therefore, you expect you will get a different number, don't you? And I think I got listen to this, 0.0065.
Dang.
Yes. I got a probability of 0.0065. A way different solution. Now, in the same interval, in the inner 10% of this interval, now the probability of finding a particle is nearly 0. It's less than 1%. So this is way different than the classical prediction, and it's way different than this prediction. So again, another good experiment. I can conceive of an experiment to make this measurement. I can clearly tell the difference between these two energy states and classical physics. Now let's go a little bit further with his comment just a moment ago and try to figure out what in the world's going on here. How can you go from having a classical prediction of 10% to a quantum prediction of either getting a 20% chance or almost no chance at all? And that's one of the real interesting questions. Well, to respond to that, I think in terms of pictures, and by the way, as a kind of a hint, this is part of the answer to someone's question earlier today. They're saying, what does it look like? That's really a good question. So I would like to start by showing in psi space, psi 1 and psi 2. Psi 1, of course, is where you have a node at each end and a single antinode in the middle. So it would look like this. It would be oscillating back and forth like this. As compared to psi 2 is 2 antinodes. With this point being the dead center, of course. But our experiment does not measure psi, but measures psi squared. So over here, let's plot psi squared in the same psi squared space and psi 1 squared when you square half the wavelength. It really just changes the shape slightly. It kind of brings these sides in a little bit and raises the peak a little bit, so it ends up kind of looking like this. And notice that we are getting a considerably higher peak in the center than anywhere else. Hence, therefore, the particle is more probable to be found in the center than anywhere else. Probably twice as likely to be found in the center. And then compare that to psi 2 squared. Well, that just happens twice. So at psi 2 squared, you end up with something that looks like this. And in the center, there's almost no probability at all. In fact, imagine this, ladies and gentlemen. At the very center of this interval, you definitely have a 0% chance of finding the particle. The particle is never in the middle. Despite the fact that the particle spends half of its time here and half of its time there, and yet it's never in the middle. How does it get there? Remember that imaginary part of the equation? It somehow goes out into imaginary space and then comes back. So it leaves the real world, goes out into imaginary space, and then comes back over here. Or another way of looking at it is that the particle itself does not exist. It's only the probability that's moving back and forth. Until you do an experiment. The experiment asks where is the particle, and the particle comes into existence when you do the experiment. You say, how often do I measure the particle here? Oh, the particle appears there. But it's not there until you look for it.
So it's just a concept that we create?
Did you say the particle is just a concept that we create? Yes. Or you could say the particle is only the result of an experiment. It's not something that, you and I have a feeling the particle is always there and then we go find it, right? It's not there until we look for it. The particle is not there. Only the probability of the particle is there. And when we go looking for it, then it appears. This, ladies and gentlemen, is the famous problem, if you've ever heard about it. It's called Schrödinger's cat. Where in Schrödinger's equation, we come up with these strange ideas. That the particle seems to spend half of its time here, half of its time there. It's never in the middle. The only logical interpretation that people put on this is that, well, then the particle does not exist. Only the probability of the particle exists until you do the experiment. All right, let's see if there are any questions. You'll notice that I did something I'm going to get rid of now, right here. That really shouldn't be there.
Why not?
Yeah.
Because it's square, it only is positive.
Oh, yes.
I just did that for fun. All right, I'm pausing for a moment to see if there are any other questions, because we've done half the problem now. We got to do the other half of the problem. Any other questions? What was the other half of the problem? This is half, what's the other half?
What is the expectation?
Expectation value, yes. Which is really quite simple, isn't it? It's just a small difference. If I'm asking for expectation value and not probability, how do I calculate expectation value? Let's go back to the fundamental definition. This is the fundamental definition of probability. What was the fundamental definition of expectation value? I'll give you a hint. You wrote it like this. That's expectation value of position. Yes?
It would be the average probability of
That sounds right, but I'd like you to tell me in an equation, and then we'll interpret it. She did the physics thing, she interpreted it. What's the equation?
the integral.
Okay, hang on. Equals
The
integral over Okay, never mind that. Integral of what?
X
X
b squared dx.
psi
Psi squared dx.
squared dx over all logical space.
Yeah.
Okay, that's a difference, isn't it? Because when you're doing probability, you're only integrating across the area of interest. Expectation value is integrated over all logical space. So, I was about to write that down and I thought, what the heck? Here is my Old Testament, that standard mathematical tables. So I made for you guys a copy of the page that I will be using, because you probably looked it up, but if you didn't, here it is. But it's G is that was since it's true like this, it's true in general. So I'm saying local value of X. Yeah, general statement. So G of X is just some point.
Oh, yeah. Expect that. Expect that. It's laughing.
Last night, I was getting so like
One I think
frustrated.
there's two there.
And I started changing the info.
Oh, why am I
Trying to
doing
figure out
this?
how to change the darkness of the screen, and I started doing the darkness. It's so bad.
Make your screen all
That
black
was
and
a
you can't
waste
see
of like 2
it.
minutes of the test time.
Oh, that was during the test?
Yeah,
Oh, wow. That sucks. I thought you meant at home or something.
it was that slight panic, like, oh my god, what am I doing? But I did this to
I
myself.
remember the tester said, I remember the thing like,
It's number 400? No, it's number 399.
Oh, that was when I read it.
Geez, I love mathematicians. They do the hard work for us. Integrating this would take a while, wouldn't it?
yeah.
But why? The mathematicians did it for us. So, we're going to do the expectation value, and we're going to use these tables because the integral is now already done for us. Let's see. What we're going to get is, first I want to make the same note. A was what? N pi over L, is that correct? And so now number 399, we're going to get that the expectation value is going to be 2 over L times this particular integral. We just factored out the normalization constant and squared it. So, number 399 says x squared over 4, x squared over 4, minus x sine 2ax, x sine 2a, n pi over L, x over 4a, minus cosine 2ax, cosine of the same thing, cosine of 2n pi over Lx, divided by 8a squared. 8a squared, evaluated between 0 and L. No, I'm not going to set that down yet. I want to check to make sure. This is where I screw up. When I'm copying things down, this is where I screw up commonly. So bear with me for a moment, and also check and make sure that you agree that I have written the correct thing. With A equals this, the expectation value is factor out the normalization constant and square it, and then we simply apply this equation. So, x squared over 4 minus x sine 2ax over 4a minus the cosine of 2ax over 8a squared. Looks like I did it correctly. And by the way, just as a subtle little criticism of some of your papers, yes, I could do this arithmetic and include the 2 in here, or I could do it anywhere in here, or I could deal with the 2 here and get rid of those. I could do that in my head. But I have found that stopping once and making sure that I plug everything in the right place at the right time and with the correct sign and everything, this is where I find my screw-ups. And it's a lot better to not do any arithmetic, no matter how simple, in your head, but rather have one line where everything is just plugged in the right place so that you can stop and have a look. That I give you as an important suggestion, especially on exams. Because I think you say, but I don't have time. I gotta get this done. And so, yes, you get it done a little quicker by eliminating one step, but you get it done wrong, so who the hell cares? Right? A couple of minutes quicker to the wrong solution doesn't count. A couple of minutes slower and get their correct solution counts. So keep that in mind. I've been looking at your papers, and you guys are really quick to do simple arithmetic in your head, but you never check this critical step. This is where you screw up just like me, and you don't want to do it. All right, so it looks like everything is pretty good here. What happens when I stick in the L? Let's find out. It's equal to 2 over L times L squared over 4 minus L sine 2 n pi over LL divided by 4n pi over L minus cosine 2n pi over L divided by 8n pi L squared.
L and 0 is going to be undefined, right?
Wait a second. Don't jump too far ahead. Now we're ready to put in the 0 minus 2 over L times, well, that's 0, right? This one is 0. And this one is 0. This is the only one which is not 0.
So that's the imaginary?
Say again?
That's the non-existent part?
This is the only part that doesn't go to 0. You see, if I put a 0 here, of course that's gone. If I put a 0 there, this is gone. All that's left is this. So, cosine 0 over 8 n pi squared over L. Oops, 8 pi over L. This whole thing is squared, not pi squared, but n pi over L squared. So that's all that's left when I stick the 0 in there, huh? And cosine of 0 is what? It's 1. Okay. Wow, what fun we have going on here. Aren't you happy? Aren't you delighted? Aren't you just pleased as they used to say, pleased as punch? Do you know who used to say that politically? No, Hubert Humphrey. Now notice, let's look here. What happens? Well, this L goes with that L, and sine of 2n pi x, which is sine of 2 pi x, or 4 pi x, or 8 pi x, or what is that? Yes?
Aren't you missing a negative?
I don't know.
Second
Am I?
part?
Yes. Let's fix that. I mean, wait a minute.
No, you're not.
No, I'm not missing a negative. Thank you. That could have been a problem in about 5 minutes. You found it for me ahead of time. Anyway, let's go back to this. What is this value? Sine of 2n pi. No matter what the n is, the sine of 2n pi is what? 0. So that term's gone. This term is 0. And of course, you'll notice that cosine of 2n pi L is what? 1. So this whole thing right here is equal to 1. So what do we have? Notice we've got 2 over L minus, here's where it is, by the way, here's where I thank you. Because look, we have 2 over L minus 1 over this creature, and then we have 2 over L plus 1 over this creature. So these guys go away. Let's do it differently. There's 0 here, and this is 0 here. Aha! So we end up with the expectation value equals L over 2. Which one were you? You asked that. See? You still have one of those terms in there, huh? I would have too if it wasn't for him.
Where did you get the cosines to turn into 0?
No, these two add to 0. These two are identical except opposite in sign. That's why I did, you see, I crossed them out this way together so that I knew this one went with that one. Those are little tricks that work. You've noticed that sometimes I like to cancel things out with color so I know what canceled what. Or sometimes I say this equals 0, this equals 1, this goes with that. Those are little tricks that really help. So we get an answer, a very, very simple answer, don't we? And the answer does not depend on n. So it was deliberate to see what you would say when I asked for the expectation value in the ground state and in the first excited state. They're all the same. The expectation value is the center of the interval. But wait a minute, how could that possibly be? Look. I wonder if it's obvious to you from this picture, is everybody looking? At this picture here, is it obvious that any time you have a state, if you have a psi that has an even number here, you're going to get a 0 at the center. Because anytime you have an even number, you're going to have a symmetric picture. If you have, let's just jump up to psi 4, it's going to go like that. And the center is always going to be 0. You're going to have 2 waves on this side, you have 2 waves on that side, you're going to get a 0. Anytime there's an even number here, you're going to get a 0 in the middle because the picture is symmetric. And yet this says, I don't care what n you have, the expectation value is the center. How can that possibly be? It's the difference between probability and expectation value. That's how it can be. The expectation value is totally different than the probability. The probability is where you're going to find it experimentally. The expectation value is what is the average position. And average is different than probability. So up here, probability is most of the time here, half the time here, half the time there. That's the probability, but the average position is the center. Even though you'll never find it in the center, the average is still the center. You know that the average doesn't have to equal any of the numbers that go into the average. And furthermore, all these pictures will be symmetric. Even the odd-numbered wave functions will have a symmetric picture. Hence, therefore, the center of the interval will always be the average position, even though half the time it's never there. Even though half the time it's never there, the center is always the end. So the other part of this problem is to keep in mind what is the difference between the probability and the expectation value. The probability is experimentally finding it. Expectation value is what's the average position. And that's vastly different. So, simple what you spent 20 minutes doing them last night? 20 minutes. Come on. You spent 20 minutes looking up this interval. Yeah, when you get into these kinds of problems, very typically, I remember as a student, as an undergraduate, we would have one problem a day. And a problem. You'll enjoy this when you get into advanced quantum mechanics. A problem was typically 8 hours. So you have one problem a day. They assign a problem, you come back the next day, and you'd spend 8 hours solving that one problem. So it wasn't quite that bad last night, though, was it? You did spend 16 hours solving these two problems. But I'll bet you spent a couple hours working on them, huh? Because half of that time, more than half of that time, was sort of, what's going on here, right? Am I correct? I mean, it's not just find a formula, stick some numbers in, and get an answer. That's not at all what it is. It's what's going on here. That's what the physicists do. All right, so here's an example of our very first problem is we solved the particle in a box. We came up with a wave function, then we used that wave function to come up with two answers. Both of them can be tested experimentally. What's the probability? What's the expectation? I'd like to go on and do a second problem now. As long as everybody's happy. I've got questions. Yes?
How do you test the expectation value?
How do you test the expectation value? Really by doing the probability experiment and finding out that it spends exactly half of its time on one side. And I don't care if you're doing this experiment or this experiment. It spends half of its time on one side, half of its time on the other. Therefore, its average position is the same. Even though not only does it not appear, it's not allowed to be there. It's not allowed to be there. Restricted so. All right, well, maybe you're seeing why, I hope you are, maybe you're seeing why I just thought this was the greatest topic in the world to discuss. Quantum mechanics is so much fun. Although quantum mechanicists are a little bit arrogant, I think. Let me tell you what I mean. My professor, one of my favorite professors was Sipun Wang, Professor Wang. He was Chinese, just arrived from Formosa, Taiwan. Very, very heavy Chinese accent. You could hardly understand him. But he was a great physicist and a great guy. Yeah.
I wanted to know when you're actually watching the particle, does it ever pass through the middle of size 3?
Watching the particle is not allowed.
Yeah.
You can only measure where is it. But by watching it, what you're saying is I'm constantly experimentally finding out where the particle is. And once you have done the experiment, you have affected the experiment, and it no longer applies. So you can't do that. These particles cannot be constantly watched. Anyway, first semester of quantum mechanics in Wang's class, here comes the final exam. The final exam consisted of only 3 questions, and one of which was this. Now mind you, I'm a senior in physics, but I'm still an undergraduate in physics, and the very first question on the final exam was, explain chemistry. All of chemistry? I need to explain chemistry. So you can see quantum mechanicists think of chemistry. You know, so you got a PhD in chemistry. That means you just barely made it past the first semester of quantum mechanics. That's what his arrogant statement was. I think quantum mechanicists are a little bit arrogant. Hey, I have a question for you. What would you imagine? What would you imagine a wave function to look like? Not mathematically, but pictorially. What would be the picture of the wave function if I put the particle in a box whose walls were not rigid? Here's the box. Here's space. Here is energy. At x equals 0 and at x equals L, I have a box whose walls only go as high as V, which is not infinity. V is some finite value. And I want to draw in here the wave functions, sort of like I did over here. But this time we do not have rigid, infinitely hard walls, but I want to draw psi, maybe just psi 1 and psi 2. I just want to draw a picture of what it would look like. What would be the difference, do you think?
And as you keep going down, it sounds back and forth.
There you go. I think you said exactly the right thing. Psi 1 would probably look something like this. Or psi 2 would probably look like this. Let me try to draw this a bit more accurately. These waves will penetrate into the wall itself. And I'm trying to show, my picture is really lousy, but I'm trying to show that I even expect, as I go further up in energy, that there should be more area here than here. That it should penetrate further into the wall. As I get closer and closer to the V barrier limit, I should imagine myself penetrating more and more. Furthermore, I don't necessarily think that this part here is actually a sine wave. This could be some kind of an exponential decaying thing that just connects to the sine wave. So, several important points. First off, we can no longer argue that there is a node at each wall. Why? The wall is not infinitely hard. The particle can penetrate into the wall a little bit. Therefore, I would have a wave function that looks sort of like this, and the important part is we've got a little bit out in this area, and as I move up in energy, I think the penetration area might be larger, and the probability and so on might be larger for each one of them. So, lousy picture, I'm sorry about that, but are the points clear and obvious? So if you have a non-infinitely hard wall, there's going to be penetration. And it's going to give you some sort of a tail on your wave function, and it ain't necessarily going to be a wave. Therefore, if I had a barrier that looked like this, here we go in energy space again, only this time I'm going to make a step function barrier. So, energy and space. And this time I'm going to bring the particle in. Notice that I have E greater than V. The particle has more energy than the barrier. Classically, we know what's going to happen. I like to think of it as a marble rolling with some kinetic energy, and this, of course, represents gravitational potential energy. If the kinetic energy of the marble is greater than the potential energy here, it's just going to roll over the hill, right? In fact, in classical physics, there's a 100% chance we're going to find a marble over here. In quantum mechanics, no. What we're going to discover is that there is a wave function to represent the particle approaching. So there's going to be a wave function like this, representing the particle approaching. There's going to be a wave function representing the particle exiting. There's going to be a wave function in between. But the last thing I want to talk about is there is a wave function to represent reflection. Two things. First, why is there a possibility of reflection? Well, it's just like light. When light strikes glass, even though glass is transparent, some of the energy was reflected. Do you remember that? There's always some reflected, some transmitted. What was it that was required for reflection? When the medium has a different optical density. Or more importantly, for us right now, when the second medium has a different wavelength. Remember, if the light sped up or slowed down, then it would split. Well, look, I indicated that there's a different wavelength drawn here. Oh, come on, did you just just draw a different wavelength and therefore, no, I know there's a different wavelength in here. Why is it that there is a shorter wavelength here and here and a longer wavelength there? Think in terms of de Broglie waves. The wavelength is related to what? In de Broglie waves, the wavelength is related to what? To the momentum, right? The momentum is related to the velocity. When the particle enters a region of higher potential energy, it has lesser kinetic energy. It must have slowed down. Its momentum is less, its wavelength is longer. Hence, therefore, I know there's a shorter wavelength here because it's faster. Same wavelength over here, same speed. In between, it slows down. Less momentum, longer wavelength. Aha! I have a change in wavelength. Some of the energy of the wave will be reflected.
So when you have an extremely hard boundary, does that mean a completely flat wavelength, or like completely, there's so many waves, it's like an infinite number?
In fact, it gets worse than that. Essentially, you've got part of the answer correct, and there's more to it. I want to show you, hopefully, a little bit later today. But yes, let me just say yes to your question now. Yes, with a caveat. There's more to come. All right. Same as light. It's interesting that the de Broglie wave behaves in a fashion similar to the way light behaves in a case like that. All right, well that's all interesting, but that's not what we're going to do. Let us consider a beam of particles incident on a barrier, only this time we're going to have the kinetic energy, or the energy of the particle, the total energy of the particle, less than the barrier height. So now, let's think one more time, only this time we're going to have a step function just like before in energy space. At x equals 0 and L, height of the thing is going to be V, and we're going to send the particle in now with an energy less than V. Again, classically, if we're thinking about the marble and the hill, if this kinetic energy here is less than the gravitational potential energy here, the particle has no chance of getting over the hill, does it? It's only going to roll up so far and come back down. That's what's going to happen classically. But now we're becoming suspicious that quantum mechanically this particle might leak through. Why? It's hitting a wall which is not infinitely hard. Therefore, the wave function and the probability will penetrate into this region. If it penetrates far enough, it might come out the other side. So there's a chance that it's going to, and I think somebody used this term on Monday, there's a chance that it's going to manufacture for itself a tunnel at the correct height. That it rolls up, and instead of stopping, it makes a little tunnel and goes right through. But it has to make the tunnel for itself. The tunnel is not there. So it's going to do some digging. It's going to do some tunneling. That's what we're going to think about. So I will constantly refer to these as regions 1, 2, and 3. Region 1 is the approach, region 2 is the barrier, and region 3 is the escape. In regions 1 and 3 there is no potential energy at all. Only in region 2 do you find potential energy. No forces act on the particle in regions 1 and 3. So, Schrodinger's equation in regions 1 and 3 is an equation that you've already seen. It's very nice, it's beautiful. It is, let me put it over here. I have to say his name because he's so important. Schrödinger. Schrödinger says, d squared psi 1 dx squared plus 2m over h bar squared v psi 1 equals 0. There's Schrödinger. V, there is no V. E. There is Schrödinger for area 1. Area 3 is going to look almost identical. D squared psi 3 dx x squared minus, plus not minus, 2m over h bar squared e psi 3 equals 0. I'm often never I am somehow this morning, aren't I? Therefore, I have to be very cautious and careful. I know I'm making silly errors. Let's check this out. D squared psi 1 dx squared plus 2m over h bar squared e psi 1 equals 0. And d squared psi 3 over dx squared plus 2m over h bar squared e psi 3 equals 0. And it says do the in-class problem here. Here's homework, so I'm not going to do this one. I'm going to do the in-class problem. This is just the one that you expect at this moment. I'm sure you expect it at this moment. Yes? You don't leave you out in the woods like that, do you?
Sure I do.
Sure I do.
Yeah.
That's the way I am. That's the way I do things. By the way, before we do that, before we give our first example problem, I want to inform you that we did not derive Schrödinger's equation. What we did was simply arrive at Schrödinger's equation. Schrödinger's equation is a first principle. There is no more fundamental principle from which you derive Schrödinger's equation. Schrödinger's equation is a first principle. All we can do is postulate Schrödinger's equation is the important equation. M, we'll notice that h nu prime, h nu plus m, h nu over c squared g h.
So there's two different.
Factoring out the h nu, we end up with 1 plus gh over c squared. Does that agree? 1 plus gh over c squared. Lovely. In 1960, two experimentalists, Pond and Ripka, working at Harvard, decided to do this experiment. And they wanted to test and see if photons do actually respond as general relativity says they must. And in their experiment, they simply